Good afternoon, my dear listeners. We continue to study the theory of electrical engineering. In this lecture, we will get acquainted with the ideal active elements of electrical circuits. At the beginning of the lecture, we will talk about what real active elements are and define the properties of these real elements. We will introduce the concept of two ideal active elements of electrical circuits, a voltage source and a current source. We will encounter these two sources constantly in the process of studying the theory of electrical engineering. We will learn about the properties of these elements as well as how a real source can be represented as an equivalent circuit consisting of ideal elements. But first, let's remember what we talked about in the previous lecture. In our previous lecture, we learned that each real element of an electrical circuit has all three properties: conductivity, inductance, and capacitance. To simplify the analysis of electrical circuits, we introduced the concept of three ideal passive elements. These ideal elements are a resistor, has only conductivity, an inductor, which has only inductive properties, and a capacitor, which has only capacitance. Such elements do not exist in nature, which is why they are called ideal. Nevertheless, as we will see later, any real element of an electrical circuit can be replaced by an equivalent circuit consisting only of ideal elements. In the last lecture, we also learned about the relationships between voltages and currents of ideal elements. These relationships are very important for future study of the theory of electrical circuits. Well, this lecture will be devoted to the idealization of active elements. First, let's look at what real active elements can be included in electrical circuits. For example, there are elements that produce electrical energy using chemical reactions for this. These are ordinary batteries and accumulators. Batteries are disposable sources. Once the battery is discharged, it is impossible to restore it. But the accumulators can be charged. In the process of charging the accumulator, electrical energy is transformed into chemical energy, and then, during operation, it can be converted back into electrical energy. In recent years, solar-powered plants have become very common. A solar power plant is an active element of an electrical circuit in which light energy is converted into electrical energy. The most widespread today are sources that convert mechanical energy to produce electrical energy. There are many of them, from mechanical flashlights to nuclear power plants. Despite the great variety of active elements, we can notice one property of in them what is inherent in all real active elements without exception. We will now turn to the study of this property. Consider the current voltage characteristic of some active element, for example, a galvanic battery. To obtain the current voltage characteristic, it's necessary to assemble the following scheme. The scheme, as you can see in this figure, is very simple. A load is connected to the battery. This is a resistor R, the resistance of which can change. This fact is shown in the diagram by an arrow that crosses out the conventional graphic representation of the resistor. By changing the resistance, we change the current through the battery. The amount of current is controlled by an ammeter, and the battery voltage is controlled by a voltmeter. The current voltage characteristics of such an active element shown in this figure. As can be seen from this graph, when the current through the active element increases, the voltage on it decreases. That is, the current voltage characteristic has a decreasing character. This behavior of current voltage characteristic is because any real active element has an internal resistance. If the current is zero, then the voltage on the element is maximum and is equal to the electromotive force of this element. When the current through the element increases, the voltage on this internal resistor increases too. This voltage is harmful because it reduces the external voltage on the element terminals. Thus, from the analysis of the current voltage characteristics, we can conclude that the voltage at the terminals of a real active element depends on its current. This property is inherent in any active element, regardless of its nature, from a watch battery to a nuclear power plant. Let us now begin to idealize the active elements. An ideal element, the voltage at the terminals which does not depend on its current, is called a voltage source. It follows from its definition that the voltage current characteristic of the voltage source should have the form as shown in this figure. Indeed, by definition, the voltage at the terminals of the voltage source remain unchanged, and it's always equal to its electromotive force. This can only be if the internal resistance of this source is zero. Indeed, in this case, the voltage drop inside the source will always be zero regardless of the amount of the current. Accordingly, all the voltage generated by the source will enter to the electric circuits without any losses. In turn, the current of such a source can be any, both in terms of magnitude and direction. Its current does not depend on the voltage at the source. This current depends only on factors external to source, that is, on the circuit to which the current voltage source is connected. if the voltage of the voltage source or its electromotive force that is equal changes over time, it is indicated by a smaller letter E, like this figure. In the case of a voltage that is constant in time, the capital letter E is used. The arrow inside the destination of the voltage source points to the clamp that has higher potential, that is to the positive pole of the source. Please pay attention to the direction of electromotive force and the direction of the voltage on the voltage source. In our first lecture, we agreed that we would always choose the direction from the positive pole of element to its negative pole as the conditional positive direction of the voltage. Thus, the voltage on the terminal of the voltage source is always directed opposite to its electromotive force. This is very important to understand and remember, because we will meet with the voltage source very often. Idealization of a real active element in the form of voltage source is not the only possible option. Now we will turn to study of another ideal active element of electric circuits. An ideal element, the current and the terminal switch doesn't depend on its voltage, is called a current source. As you can see from this figure, the current voltage characteristic of such a source is a straight line perpendicular to the voltage axis. The current through the current source is constant and doesn't depend on its voltage. In turn, we can say that the voltage on such a source also does not depend on its current and can have any magnitude and any direction. Any magnitude, any direction. This voltage depends only the parameters of the electrical circuit to which the current source is connected. The conventional graphic designation of the current source is shown in this figure. The direction of the current generated by the current source is shown by the arrows on this figure. Let's look again at the current voltage characteristic of the current source. As you can see, the current of this source remains constant and doesn't depend on the parameter of the external electric circuit to which the source is connected. At any resistance of this circuit, the current is constant. This is possible only on the condition that no matter how large this external resistor is, it will still be much smaller compared to the internal resistance of the source. That is, the internal resistance of the current source is infinitely large. Thus, we have idealized a real active element with some internal resistance of its own, using two ideal active elements. This will allow us to build equivalent schemes for a real active element. Any real active element on an electric circuit can be equivalently represented by two equivalent schemes using either a voltage source or a current source, as you can see on this slide. As we already know, every real active element has an internal resistance. Therefore, we can model the properties of a real element in two ways. First, you can use a voltage source with a resistor connected in series, which is shown in this scheme. In this case, the electromotive force of a real active element is simulated by a voltage source, and the internal resistance of a real source is simulated by series connected resistor. The same effect can be achieved by using a current source instead of a voltage source. However, the internal resistance of current source, as we already know, is infinitely large. Therefore, a resistor simulating the internal resistance of a real source must be connected in parallel to the current source, as it's shown in this scheme. Please note that one real active element is modeled with two ideal ones. That is, this equivalent scheme is complicated. But, as we will see later, thanks to the ideality of elements, its analysis will not be difficult. Both equivalent schemes simulate one real element. Therefore, we can assume that they are closely related to each other. For example, by knowing the parameters of a circuit elements with a voltage source, we will be able to determine the parameters of the circuit with a current source. We will return to this when we study the equivalent transformations of electric circuits. Our lecture has come to an end. Let's summarize what we have learned. Now we have known that any real active element in an electrical circuit has internal resistance. Therefore, the current voltage characteristic of a real active element has a decreasing character. The current through the element increases and the voltage across it decreases. We learned that we can offer two ideal active elements, a voltage source and a current source. The voltage across a voltage source is independent of its current, and the current of a current source is independent of its voltage. The internal resistance of the voltage source is zero, and this resistance of the current source is infinitely large. Any real active element of an electrical circuit can be represented by an equivalent circuit containing either a voltage source or a current source. We will encounter voltage source and current source very often when analyzing electrical circuits. Thank you so much for your attention. Have a nice day. Goodbye.